In order to determine the maximum magnitude of the bending moment given by the variable m that can be applied to the beam so that the bending stress in the member does not exceed the value of 12 ksi, we can start by first resolving our moment along the y and z axis. Since the moment that is given to us is making an angle of 45 degrees with respect to the z-axis, so we can project it along the z-axis by multiplying it with cos 45. This will be the value of mz. Similarly, in order to project that moment across the y-axis, we take the function of sine 45, and that will project it along the y-axis pointing downward in the counterclockwise direction. Now let's go ahead and simplify these values. Cos 45 and sine 45 are equals to one another and have a value of 0.7071. So our mz value and my value will be equals to 0.7071 times m. Now, once we have the bending moment along the y and z axis, let's go ahead and write our formula to calculate the bending stresses, that is given as sigma equals to m times c over I, where m is the bending moment, c is the distance from the neutral surface to the furthest point away from the neutral surface, since we are calculating the maximum value of stress, whereas I is our moment of inertia. Since I have moment acting along both my y-axis and z-axis, I need to calculate this geometric property along the y and z axis, that is basically providing the resistance against the rotation. So let's go ahead and draw the cross section of the beam. Here I have a hollow rectangle channel where my dimensions of the outer rectangle is 16 inch by 10 inch, whereas the rectangle dimensions are 14 inch by 8 inch. So in order to calculate the moment of inertia along the y and z axis, we can utilize the formula of 1 over 12 bh cube that is utilized for any rectangular section. Now, in this case, what we will be doing, we will be calculating the moment of inertia of bigger outer rectangle and subtracting the moment of inertia of the smaller inner rectangle out of it. Now, once we are calculating Iy, the value of B will be parallel to the y-axis. So for a bigger rectangle, that value is 16, whereas the height h is equals to 10. Similarly, for the smaller rectangle, the value of b will be the one that is parallel to the y-axis, that is 14 times 8 cube. Simplifying, we get the value of Iy equals to 736 inch raised to power 4. Similarly, we can calculate the moment of inertia about z-axis utilizing the same formula. Again, the value of b now in this case will be the dimension that is parallel to the z-axis. So for a bigger rectangle, the value of b is 10 and h is 16 cubes. As for the smaller rectangle, we have the value of base as 8 inches, whereas the height is 14 inches. Simply, we get the value of IC as 1584 inch raised to power 4. Now, once we have the I value, let's go ahead and look at the cross section and try to identify at which one of these points A, B, C, and D we will be experiencing the maximum value of stress. Now, keep in mind we have my and mz. We have to keep in account of both of their effect. So starting with my, now since it is in the counterclockwise direction along the y-axis, meaning that in the quadrant where point D is, the stress value will be in tension, whereas where point A is, it will be in compression as it is pushing down towards that specific section. Similarly, for MC, we will have our tensile stresses on the section of the beam that is above the z-axis where our point B and C lies, whereas where the point A and D lies, it will be in compression. So if you look at point A, both My and Mz have the compression stresses acting on it, whereas if you look at point C, both My and Mz are going to cause the tensile stress at that point. Now, if you look at point B and point D, for point B, My is going to cause a compressive stress at point B, whereas the Mz, that is moment acting along the z-axis, is going to cause the tensile stress. Whereas at point D, we will have the same scenario where My is going to cause the tensile stress at point D, whereas Mz is going to cause the compression stress at point D. So by inspecting all of the points, the maximum tensile stress that will be present on the cross section of the beam will be at point C. So since we are looking for the maximum tensile stress value, so the value of a stress at point C will be the sum of My times YC divided by IY plus Mz times ZC divided by IZ. Now in this case we are looking at the combined effect of both of the moment of My and Mz at point C. Now, since in the question it is given to us that the maximum stress in the member should not exceed to the value of 12 ksi, so replacing sigma c with 12 ksi, plugging in the value of My as 0.7071 m times yc, that is a distance from the y-axis to point C. In this case it's coming as 5 inches divided by the moment of inertia about the y-axis of 736 plus the value of My, that is again 0.7071 times m times yc, that is a distance from the z-axis to point C. In this case the value is 8 inches divided by Iz, that is 1584. Now here we have an expression where only one variable is unknown, that is m. We can simplify and solve for the value of m, that is coming as 1433.7 kip inch. Now in order to represent it in terms of feet, we need to divide this number by 12. So the value of moment is equals to 119.4 kip feet.